Okay, your question. Um, an oil pipeline carrying crude 100,000 barrels per day. So that implies that it's a single phase flow carrying hydrocarbon. So, despite the fact that hydrocarbon is multi-phased, but the produced crude is a single, assuming that it's dry crude, it's a single phase fluid. So for single phase fluid, let's first of all establish the governing equations applying to the determination of the losses within a closed conduit carrying a closed system carrying fluid under steady state conditions. Okay, so a closed system carrying fluid under steady state condition. Now, so the fluid is flowing in this direction, and then the fluid, assuming that the profile is steady throughout the vertical cross section of the closed system, in this instance a pipe, and then you have the fluid exiting at a different pressure. So that's P1 and this is P2. So assuming the cross section is the same, so assuming that this line is horizontal, not elevated, based on the question that was sent, assume that the topside entry and shore facility elevations are the same. Let's determine what the governing equation associated with the flow of this fluid through this pipeline under steady state condition. So as the fluid flows, you have some losses, so you have some friction forces on the walls. So if you sum the forces in the horizontal direction of flow, so let's assume that that's the x direction. Under steady state condition, the summation of forces in any direction will be equal to 0. So this is Newton's second law. Okay, it's called the impulse momentum equation in fluid kinematics. Now, so the summation of forces in the horizontal direction is equal to 0. So this implies that P1 A1, so that's the cross section of this area, right? Then minus, so you have your area vector pointing in this direction. Okay, so minus P2 A2, right? Then minus, so you have friction inside the walls of the flowing system. So the friction forces will oppose the flow of motion. Okay, so minus, I call it FR, friction force, is equal to mass times acceleration dv dt. Okay, so let's call that as one, equation I. Now, this friction force, FR, is equal to the shear stress of the fluid, okay, times the wetted perimeter. Okay, so times the wetted perimeter times the length of the flow section. So let's assume that the flow section is L, right? So the shear stress, the shear stress within the fluid flow layers times the wetted perimeter times the flow length, which in this case I indicate as L. Right? Now, from laboratory studies, it has been shown that the shear stress of the fluid layer is directly proportional to the square of the flow velocity of the fluid within the closed controlled volume. So this implies that the shear stress will be equal to K times V square. Okay? So the shear stress is equal to K times V square. So if you substitute that in the expression for the friction force, you have the FR becomes what? KV square times PL, right? KV square times PL. So let's back substitute into expression 1. If you back substitute this into equation 1, you will have that. So back substituting, you have that P1 A1 minus P2 A2 minus KV square PL is equal to what? The M dV dt, right? Note that V is equal to the velocity of flow. Okay. So changing velocity of flow within the closed system. So assuming that the flow is steady state condition, it means that the V becomes 0. So acceleration is equal to 0. And then the cross section is the same. If the cross section is the same, this equation then becomes A into P1 minus P2, right, is equal to what? KV square PL. Okay? So A into P1 minus P2 is equal to KV square PL. Let me save this as image 1. Now, okay, so we say AP1 minus P2 is equal to KV square PL, right? So I just said that A into P1 minus P2 equals KV square PL. Let's divide both sides by the specific weight of the fluid. Let's divide both sides by the specific weight of the fluid. You have that A. Alright, so you have that A into P1 minus P2 over this equals KV square PL over the specific weight of the fluid. Right? So it implies mathematically that P1 minus P2 all over that is equal to what? KV square PL all over what? A times the specific weight. So let's call this one equation 2. Now, remember the same control volume that we looked at. So remember, this is the same control system. So if you apply Bernoulli's equation between any two arbitrary points, okay, this is called the energy equation, and take a reference datum, and that we call that as Z1 and call that as Z2. Okay, the total energy along a streamline is constant, right? So the total energy per specific weight, so P1 over that one plus V1 square all over 2G plus Z1, okay, equals P2 all over the weight of fluid plus Z2, right, plus V2 square all over 2G. Then plus you're going to have some significant pressure drop. So plus what? The head loss due to friction in the pipe, HF, right? Now, because the elevation is the same based on the question you sent, elevation is the same, good. So elevation is the same, and the fluid is assumed to be incompressible. So if it's incompressible, the density is the same at inlet and exit, right? So the density is the same at inlet and exit. Then it implies that P1 minus P2 all over the specific weight, and then under steady state condition, the velocity is the same. So V1 is equal to V2, so that cancels that, right? So P1 minus P2 over this is equal to head loss to friction. So the head loss due to friction is the pressure drop per the specific weight of the fluid. Therefore, if you look at equation 2, it means that the head loss due to friction equals KV square, okay, PL, all over what? A times specific weight. Now let's call this equation 3, and let's save this. Okay, let me save that. Good. So head loss diffusion is equal to KV square PL all over A times the specific weight. Keep that in mind. Now,